Now I want to look at curl in R3 space. In 2 dimensions, curl gave me the measure of the rotation of a vector field at a point. The circulation form of Green's theorem implies that if the 2-dimensional curl of a vector field is 0 throughout a simply connected plane region, then the circulation at the boundary of the region will be 0. And if the curl is non-zero, then Green's theorem will give me the circulation along the curve. In 3 dimensions, curl becomes the cross product of the del operator and f, where f is the vector field given by a vector with components fgh, and it involves computing the determinant of a 3x3 matrix, so that del cross f is equal to the determinant of a 3x3 matrix where the first row is populated with I hat, j hat, k hat, the second row is populated with the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z, and the third row is populated by f, g, and h. This determinant becomes the partial of h with respect to y minus the partial of g with respect to z in the I hat direction, plus the partial of f with respect to z minus the partial of h with respect to x in the j hat direction, plus the partial of g with respect to x minus the partial of f with respect to y in the k hat direction. The third term is the rotation parallel to the xy plane. The middle term is the rotation parallel to the xz plane, and the first term is the rotation parallel to the yz plane. Geometrically, I can set up a 3-dimensional coordinate system and look at plotting streamlines for a vector field. If I choose one point on my streamline of my vector field and superimpose a coordinate system that is parallel to the x, y, and z axes that I already have, the I component of my cross product gives me the rotation parallel to the yz plane. This is a rotation about an axis that's parallel to the x-axis. The j component of my cross product gives me rotation parallel to the xz plane. This is a rotation that is about an axis parallel to the y-axis. And the k component of my cross product gives me rotation parallel to the xy plane, which is a rotation about an axis parallel to the z-axis. The curl of a vector field, f is equal to a vector with components fgh, that is differentiable on the region of R3, is given by the curl of f is equal to del cross f, which is equal to the partial of h with respect to y minus the partial of g with respect to z in the I hat direction, plus the partial of f with respect to z minus the partial of h with respect to x in the j hat direction, plus the partial of g with respect to x minus the partial of f with respect to y in the k hat direction. If del cross f is 0, my vector field is irrotational. A general rotation field is given by f is equal to a cross r, where a is the vector with components a sub 1, a sub 2, a sub 3, and it is a non-zero constant vector, and r is the vector with components x, y, z. F can be written as a cross r, which is equal to the determinant of a 3x3 matrix, where my matrix is populated in the first row by I hat, j hat, k hat, in the second row by a sub 1, a sub 2, a sub 3, and in the third row by x, y, z, and my determinant becomes a sub 2z minus a sub 3y in the I hat direction, plus a sub 3x minus a sub 1z in the j hat direction, plus a sub 1y minus a sub 2x in the k hat direction. This vector field is called the general rotation field in 3 dimensions. Notice that if I let a sub 1 and a sub 2 both be 0 and a sub 3 is 1, this reduces to the 2-dimensional rotation field given by a vector with components negative y, x, with its axis in the k hat direction. Similarly, we could let any other pair of my components be 0 while the third is 1, and we would get 3 distinct two-dimensional rotation fields. This means that the general rotation field in 3 dimensions is the superposition of 3 rotation fields with axes in the I hat, j hat, and k hat directions. When I superpose these 3 distinct vectors, I get a single rotation field with an axis of rotation that is in the A direction. There's a little bit more that I want to say about the general rotation field. If I compute del dot F for a general rotation field, we get del dot F is equal to 0. And this tells me that the divergence of the general rotation field is 0. Also, if I compute del cross F for a general rotation field, I'm going to get del cross F is equal to 2 times A. This tells me that the curl of the general rotation field is in the direction of A. The magnitude of the curl gives me the magnitude of del cross F, which is equal to the magnitude of 2A. We will see through some problems we'll work with that the magnitude of A is the angular speed of rotation of the vector field, which we typically denote by omega. This is the speed at which a small particle in the vector field rotates about the axis of the field in units of radians per unit of time. So that the magnitude of del cross F is equal to 2 times the magnitude of A, which gives me the constant angular speed of rotation, omega, is equal to 1/2 the magnitude of del cross F. The general rotation field is F is equal to A cross R, where the non-zero constant vector A has components A sub 1, A sub 2, A sub 3, and it is the axis of rotation. R is the vector with components x, y, z. For all non-zero choices of the vector A, the magnitude of del cross F is equal to the magnitude of 2 times A, and del dot F is equal to 0. The constant angular speed of the vector field is given by omega is equal to 1/2 the magnitude of del cross F. So let's work an example. If F is given by a vector with the components 1, -2, -3 crossed with a vector R, we want to find the curl of the vector field assuming that R has the components x, y, z. We want to confirm that my curl is in the same direction as the axis of rotation and compute the constant angular speed of rotation. So that F is equal to the vector with components 1, -2, -3 crossed with R tells me that my vector A has components 1, -2, -3. So that now all I have to do is compute the determinant of my 3x3 matrix with the first row populated with I hat, j hat, k hat, the second row populated by 1, -2, -3, and the third row populated by x, y, and z. I get -2z plus 3y in the I hat direction, plus -3x minus z in the j hat direction, plus y plus 2x in the k hat direction. Del cross F becomes the partial of y plus 2x with respect to y minus the partial of -3x minus z with respect to z in the I hat direction, plus the partial of -2z plus 3y with respect to z minus the partial of y plus 2x with respect to x in the j hat direction, plus the partial of -3x minus z with respect to x minus the partial of -2z plus 3y with respect to y in the k hat direction. This gives me 1 plus 1 in the I hat direction, plus -2 minus 2 in the j hat direction, plus -3 minus 3 in the k hat direction. The simplified vector form is 2 I hat minus 4 j hat minus 6 k hat. If I factor out a common factor of 2, I get 2 times the vector with components 1, -2, -3. This tells me that my curl is in the direction of the axis of rotation, and the axis of rotation is the vector A with components equal to 1, -2, and -3. My angular speed omega is given by 1/2 the magnitude of del cross F, which gives me the square root of 14. Now you try it. Pause the video, and given the vector field F is equal to the vector with components 3x z cubed e to the y squared power, 2x z cubed e to the y squared power and 3x z squared e to the y squared power, calculate the curl of the vector field. When you're ready, restart the video to check your understanding. So I need to find del cross f. I know that del cross f is the curl of f, and I can write that by taking the partial of h with respect to y minus the partial of g with respect to z in the I hat direction, plus the partial of f with respect to z minus the partial of h with respect to x in the j hat direction, plus the partial of g with respect to x minus the partial of f with respect to y in the k hat direction. Del cross f therefore becomes the quantity 6xy z squared e to the y squared minus 6xz squared e to the y squared in the I hat direction, plus 9xz squared e to the y squared minus 3z squared e to the y squared in the j hat direction, plus 2z cubed e to the y squared minus 6xyz cubed e to the y squared in the k hat direction. I'm going to factor out a common factor of z squared e to the y squared, and I get z squared e to the y squared times the vector with components 6xy minus 6x in the I hat direction, plus 9x minus 3 in the j hat direction, plus 2z minus 6xyz in the k hat direction. This is how I can work with curl in 3 dimensions, and in particular, it shows me how to work with a general rotation field. Be sure and let me know if you have any questions.